Chapter 1: Stress, Normal, Shear and Bearing Stress. In this example, we want to study we want to calculate the reactions in at the supports like we have two support A and C here, so we want to have the AX AY component of CX CY for the forces at reactions, and also we want to calculate, after calculation of forces, we want to know what the normal shearing and bearing stresses are in this configuration. Data provided is a this configuration consists of a boom at AB, which lies from A to B, and a cylindrical rod extended from B to C, which handle a 30K downward concentrated load at pin C. The dimensions of boom and rod and also diameter of pins are at B, A, and C are provided. The very first step in such problem is drawing a free body diagram which releases the support and just see the effect of forces on the structure. So that's how we see this a x and y component at reactions like Cx, Cy, Ax, Ay, and the concentrated load from problem statement at pin B. If we develop a moment, for example, about point C in this figure, so summation of moment about point C goes 0, it just gives us Ax times the vertical distance from point C, which is 600 millimeters or zero point 0.6 meters, minus the other force is this concentrated load of 30K, a vertical distance to C of 800 or zero point 0.8 meters. So if you do the math, it just gives you Ax is a tensile force of 40K, and summation of forces in x direction, it just says Ax should cancel out by Cx. So Cx is a negative Ax, and Cx is the same numeric value in the different in the other direction, opposite direction. Summation of forces in y direction goes 0. It just gives us that Ay and Cy, the two component of vertical forces, should cancel out the downward force at being B at pin B. So Ay plus Cy goes 30 is equal to 30 kilonewtons. And if we develop another moment uh, based off point B, so the summation of moment about B goes 0 this time. Summation of moment about B goes 0. It because the force of rod, all these two components translate to a resultant force at bar BC, and they all, as you can see, they just passes through pin B, so they exert no moment about B. The only component which the same story for AX, it passes through B, so no moment. The only component which develop a moment about B is AY, so a negative AY due to our direction of counterclockwise is a positive direction, and negative AY times 0.8 meter goes 0. It just gives us AY is 0. If you replace it in previous equation, which AY plus CY goes 30, and it just says AY, if AY is a 0, so CY is 30 kN. So far we do know AX is a 40, and in x positive x direction, Cx is a 40, but in negative x direction, because that's a negative, and Cy is a 30 kilonewton in upward, because canceling the 30 kilonewton downward at B. So if, for example, Ax is a positive x direction, it pushes the pin at A. So the same story happens to the member. So it just says a boom AB is a compressive force. Likewise, if Cx, which is a negative x direction, so it just pulls the pin. It should do the same. Mhm. It should do the same to the member as well. So rod BC is a tensile force. So far, we do know the direction of forces inside the boom AB and rod BC, but yet we have to calculate the numeric value for them. If you apply the sine law for the forces based off point B, which AB applies there, BC applies there, and 30 kilonewton downward force applies there. So sine law in forces says FAB, force at AB, over 4 is equal to FBC over 5 equal to 30 kilonewton over 3. If you do the math, you can get both unknowns. We already know the direction for the forces. This time we calculate the numeric value of force AB and BC, which is if AB is a negative 40 kilonewton and BC is a positive 14K it's a tensile force. As soon as we have the forces, we can calculate the stresses, but let's see how we can interpret them in different kind of stresses. So let's start from normal stress at rod BC. So if we already know FBC, rod BC has a tensile force of positive 50 kilonewton, and the area of BC is just a cylindrical with the diameter of 20 millimeters. That's a pi times d squared over 4. That's a quarter of pi d squared, and that's a 314 times 10 to negative 6 meters squared. And definitely the stress is force over the area, and if you do the math, it gives you 159 in terms of megapascal. Mhm. Yet, if you have a closer look to rod BC, you can easily see in the flat part of the rod is under tension as well, but you do need to go for the narrowest section. That's the concept of a net. How is that? So for example, as you can see here, so this distance is 40 millimeters. Diameter of pin, which is, do you remember all the pin has a diameter of what? A 25 millimeters. So a net goes by a diameter of our rod, which is 20, and that's this part. That's the thickness if you pay attention. That's a 20 millimeters. This time times 40 minus 25. That's a concept of a narrowest section close to the support. So that's 40 minus 25, 25 times 20 millimeters, which is the thickness of our thickness is the diameter of rod BC. That's our net area. Mhm. So A net is again 20 millimeters times 40 minus 25, which gives you a 300 times 10 to negative 6 meters squared. And stress in BC is just FBC over this time net cross-sectional area. So we have two part of calculation for normal stress in rod BC. One is close to support and one is in throughout the entire section of rod from B to C. So this time sigma BC is 167 megapascal, and definitely that's a sigma average. Mhm. Let's calculate normal stress in boom AB this time. Boom AB is a rectangle with a dimension of 50 mhm, in length and 30 millimeters in thickness. So that gives us this much of area, and FAB, which is a negative 40. We already calculate the force in both of them. It was the rod has a positive 50 kilonewton force, and boom AB has a negative 40K compressive force. So stress at boom AB is force over the area, we get the area, and if you do the mass, it just gives you a negative, because force was a compressive force, a negative 26.7 megapascal. Mhm. Let's calculate the shear stress and start from the top, which is a pin at C. So if you pay attention to the figure, you can simply see the 50 tensile force applied to a single shear scenario. Mhm. And a pin at C is just pi times diameter of pin squared over 4. So that's a 25 squared over 4 times pi, and that gives you this much of area. Uh-huh. And if you go for tau at pin C, that's a force of 50 over area of pin, which is 491 10 to negative. And if you do the math, it gives you a positive 102 megapascal. Mhm. Let's attempt the calculation of shear in boom AB. And if you look at that's a top view of boom AB. That's a top view of boom AB, mhm, which you can easily see that's in a double shear two section. Mhm, mhm. And that's a side view of boom AB again. That's a side view of boom AB, which handles the 30K downward force at the end, which is B. And again, you can easily see B, the far end is also in double shear. From this figure, you can easily understand that's the the other part, the other far end is also in double shear. So let's see how that goes. Yet we know the force in boom AB is a compressive force. Mhm. So let's attempt the shear in pin A, for example, here. This is pin A with a diameter of 25 millimeters. Mhm. And we know the dimension, and that's a 40 compressive force. Mhm. If you translate that in a double shear scenario, it just says that's a 40 applies or convert to two forces. You can interpret it in either way, either force over half of the area or half of the force over the whole area. So that's a interpretation of the half of the force over the area. And force of the area of the pin are identical to other pin, which is a quarter of pi 25 squared, and P, which is 20 kilonewton, half of that, because of the effect of double shear, it just gives you a 40.7 megapascal. And definitely that's due to double shear condition, which you can easily see here. Mhm. That's a top view of pin B at the far end. And let's take a closer look at pin B. You can easily see it consists of 5 parts. 2 part for boom AB, mhm, one for rod BC at the center, and two for brackets. Mhm. Because it's a long pin connecting all the other uh, pieces together. So by that I mean, for example, central section just connected the rod BC to the C. Uh-huh. These are related to double shear of boom AB. Uh-huh. It's a kind of connected to boom AB. And this part is a connected to a bracket. So let's see, these are the boom and these are outer part is the bracket one. Mhm. Then let's see how we can attempt our problem. Mhm. So if you take a closer look to that, you can easily see, well, this is a half of the 30 kilonewton applies at this part, half of the other applies at this part. FBC of rod is 50 applied at this part, and each of those 20 kilonewton, which is the compressive force of boom BC, boom AB, which is a negative 40, it just apply to the pin B. And that's pin B. In that sense, one can say due to symmetry, due to symmetry, PG is equal to PH. This is G halfway through, and that's PG. And we have half of this 50 applies to the right, and the other due to symmetry to the left. So we can just go by half of the force at the rod. So in that sense, average shear at B is 25, our area of pin, and that's again a positive 50.90 megapascal. The other part is calculation of bearing stress at A in boom AB. So this is A bearing stress at A in boom. So if you, this is the boom. If you want to see the effect of bearing stress in A in boom, just close this part, open this part. So it just says for bearing stress at A in AB, you can easily say I do have a 40 kilonewton, which is the compressive force of 40 here times a, because we are working with the boom, we are at A, but we are in the boom. So we need the cross-sectional area of boom. That's 30 times 50. And that gives us a positive 53.3 megapascal. That's the thickness is 30 and diameter is, and that's not diameter, that's a, yes, that's correct. That's a diameter of 25 in A. Mhm. That's a 30 thickness times the diameter of our a pin at A. And if we want to calculate the bearing stress in bracket A, it just gives us a sigma B, which is 40K, again 40 compressive force over this time a 50, which is this part plus this part, again times the diameter. All the time in bearing stress, we are concerned at our diameter at uh, our pin at A. Likewise, this time or either this scenario or the previous one, we are concerned with the area which is related to the part which related to our appropriate area of our pin. Thank you. That was a complete example of effect of different stresses on a configuration of forces. Thank you.